Today's video is a continuation of day one of arithmetic sequences, but now what we're looking at is what if we want to add them all together. So that's why here in our title we're talking about the sum. So an arithmetic sequence can be 1, 2, 3, 4, etc. because it's all increasing by 1. So what we're going to look at today is what if we wanted to add all of those together. And you'll see later there's many real-life examples why we would want to add those together and save some time. So there's some nice easy formulas that go with it, but before we give you the formula, we're just going to explain where it came from. What we're talking about here is many years ago there was a 10-year-old boy, his name was Carl Gauss, and he was asked by his teacher to add from 1 to 100. So if you had 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 100 laid out, and add all of those numbers together, what the answer would be. And what this particularly bright student realized, if you wrote them backwards, so he wrote from 1 to 50, and then he wrote from 100 down to 51, and added them, 101, 101, 101. They all added up to be 101, so that means 50 times you had 101. So he found a really fast way of adding all of those numbers together. So first of all, what this is asking us here, that how many hundreds and one are there? There's 50 of them. So you can multiply those together. How can you determine the 50? It's always going to be half of the number of the terms. So there was 100 terms here, we divided it by 2. And how can you determine the 101? You just take your first number and your last number and add them together. And that's what this says here. So that's some note for you if you would like to copy down. It's not really testable material, but it just gives you a sense of where our formulas come from. So let's look at this here, because I'll highlight it. Our first formula we're going to deal with, that S at n means sum of the number of terms. So we can obtain a general formula by taking half the number of terms, so that's where the n divided by 2 is. So if we were looking for the 100 terms, we divide it by 2. And sum of the first and last terms. That's why we have A being initial and T at n being the last term. For example, term 100. S and n representing the sum of the first n terms of the series. So this formula is great and helps us out as long as we know how many terms, the first term and the last term. But we can come up with another formula here that's also going to be very helpful for when we don't know the last term. So if we took the formula we knew, I'm going to do some work up here so you can see it, n divided by 2, this was the original formula that was derived from our example of the story of Carl. I know that T at n, that equation is equal to a plus n minus 1d from day 1. So if I substitute that in, n divided by 2, a plus a minus n minus 1 d. Again, this here is what t at n was equal to on day 1. So all I'm doing is deriving another formula that will also be helpful for us. So I have two a's there. And then I'm left with plus n minus 1d. So that's what this is here. This is just what I did here in rough, is just showing you where it came from. These two formulas are what you're going to have to use to solve. The first one, this was this here, the first version is useful when you know the last term and the common difference. The second version is useful when the common difference is known, when you know what d is, but not the last term. So as you go through the examples, you'll see quickly when you need each one. So we'll do a few quick examples and then you can complete the rest of the work in class tomorrow. So we have a pattern here. So let's just say our pattern is 3, 9, 15, 21, etc. So we don't know the last term. We don't know what t at n is equal to. So if we wanted to find the sum of the first 50 terms, we don't know t at 50. So it's better for us to use the second formula, 2a plus n minus 1 d, because we have all of the information. We know what d is, we know what n is, and we know what a is. Just going to make a little bit more room here. So we can substitute in. So if I'm looking for the sum of the first 50 terms in this pattern, I have 50 divided by 2. You can go right to writing 25 there. Our initial term is 3. 2 times 3 is 6. Then we have 50 minus 1 is 49. And I know my difference between every term is 6. So again, when you're substituting in there, you might have it look like this last line right here so that it's a little bit faster. You don't need this step here necessarily. So then to finish the question off, we have 25 multiplied by 6 plus 294, which is 25 times 300, which equals 7,500. So therefore, S at 50 is 7,500. So if we wrote out the sequence and all of the first 50 terms and added them together, the sum would be 7,500. So in this example here, we'll look at the second example. You can finish it and bring it into class tomorrow. You need to find the sum of the series 5, 8, 11, so forth and so on, all the way up to 182. So what we see is that it's increasing by 3 all the way along, and we know, so it's increasing by 3, d is 3, and we know that t at n is 182. We don't know how many term numbers there are, but we do know that that t at nth term is 182. So do your best to substitute into the equation and see if you can solve it. What the trick is here, when you come into class to show me the work, be sure you have it, is that you have to solve for n first. So see if you can do it, and then we will continue in class from there.